Okay, in this lesson, we're going to look at catalyst. And so let's go ahead and define what a catalyst is. A catalyst is a substance which increases the rate of a chemical reaction without being consumed by the chemical reaction. And so it's important to understand that a catalyst is not a reactant. In a chemical reaction, reactants are converted into products. Catalysts do not convert into products. They are not a reactant. They are not a product. They are simply in the reaction, helping the reaction proceed. They're not consumed by the reaction. So the catalyst that you begin with is the exact same thing that you end up with at the end of the reaction. Now, it may be changed during the reaction, but when it's all said and done, if it's changed back into what it originally was by the time the reaction is completed. And so that's what a catalyst is. How does a catalyst increase the rate of a reaction? A catalyst will increase this rate of reaction by providing an alternate reaction pathway with lower activation energy. And so the fact that the activation energy is lower is going to allow more reactant particles to collide with sufficient energy in order to react. And so this is what a catalyst is. You need to know the definition of a catalyst. You need to know how a catalyst works. And then you're going to need to know some relations to some of the graphs that we've already looked at. So let's look at those and let's introduce the concept of a catalyst into those graphs. And so here is an example of a graph that you've seen before. This is an enthalpy level diagram between reactants. Say we have reactant A turning into product B. And so reactant A has this level of enthalpy and product B is down here. And so you would know from previous topics that this is an exothermic reaction. We are releasing energy, a net change of energy from here to there. And so that's a negative delta H change, so exothermic. But this little hump here, I believe we talked about this before, this little hump here, that is the activation energy. And so this reaction will not proceed unless the reactant particles can get above that little hump there. That's the energy of activation, or the activation energy. Now, what a catalyst does is it takes that hump and it lowers it. It provides an alternative pathway of lower activation energy. And so instead of having to get all the way up there, the particles only have to get up to this smaller hump, and that's going to allow more particles to collide with sufficient energy in order to react. And so if you're drawing an enthalpy level diagram with and without a catalyst, well, the catalyst hump is going to be lower than the uncatalyzed reaction will be. And so that's a graph you need to be able to recognize and be able to duplicate in regards to the action of a catalyst. You should also be able to look at it in light or in the eyes of a Maxwell-Boltzmann curve. And so if you remember, a Maxwell-Boltzmann curve is a graph that will plot kinetic energy versus number of particles, and it relates to temperature. And so if we have a Maxwell-Boltzmann curve, there's our curve. This would be our AKE right there, which would be a direct measurement or an equality to the temperature of that substance. And remember, in the postulates, the particles have to have sufficient energy to react when they collide. Well, which particles in this graph have lots of energy? Well, it's the particles up here on the right side. They're the ones that have lots of energy. And so we could maybe say, or draw a little line here, right there. If they are to the right of this line, then they have sufficient energy to overcome the activation energy if they collide. So if two particles up here collide, then they would have enough energy to react. If two particles down in this area collide, they're not going to have enough energy to react with each other. And so this would be uncatalyzed. If we add a catalyst, what happens is we bring that activation energy down lower. And so now you can see that in addition to this percentage of particles that have sufficient energy to react, we've now added this percentage of particles that have sufficient energy to react. So a higher number, a higher percentage of our reactant particles now will have sufficient energy to react in order to facilitate a faster reaction rate. And so that is what the activation energy there is going to do when we look at it that way. Now, I do want to also look at the Maxwell-Boltzmann curve. When we talked about it earlier, I didn't quite get to all of it. I want to look at a couple other graphs with the Maxwell-Boltzmann curve. A couple other different graphs. So there's a curve, and there's a curve, and a third curve. And so what we have here is we have three substances at three different temperatures. In relation to each other, this was at a low temperature. The red one is at a high temperature, and the white one is at a medium temperature. When you heat up a substance, more and more particles begin to move faster, and so for example the red curve, more of the particles shift over to the right side, and so that the height of this curve begins to get stretched. We begin to pull it to the right, we begin to stretch it out, and so it's like we're just grabbing hold of this little string right there and we're pulling to the right, and so everything flattens out. Now the volume, if you measure the volume mathematically, the volume of these three humps underneath the curves will be the same. And so if we're going to move to the right, we've got to lower the peak to make the volumes the same. Conversely, if we cool it down, these particles on the right side begin to move back to the left, and we begin to scrunch it or squeeze it, and the peak rises. And so if you're asked to evaluate Maxwell-Boltzmann curves, different Maxwell-Boltzmann curves in relation to each other, then that's just an easy evaluation between low, medium, and high temperatures. Or they could give you one and say, hey, what would it look like if the temperature was increased? Well, take the curve that's present and then flatten it out and elongate it to the right. Or, hey, here's a curve, the white curve. What would it look like if you cooled this substance? Well, squeeze it to the left. You're going to make the peak go up, and you will get a shorter curve that way. Now, in relation to reaction rates, how does this also equate? So let's say that this is our point right here. Remember, this is energy on this scale. This is our point of activation energy right there. Okay, well, if you look at the colder substance, you have very, very few molecules that are to the right of that point. If you look at the warmer substance, you have a much larger percentage of molecules to the right of that point. And so this is why increase in the temperature of a substance increases the rate of the reaction. Several factors are involved, but one of those factors is the fact that more and more particles, a higher percentage of the particles that are in that substance will have sufficient energy if they collide with proper orientation in order to react. And since more particles have that, more percentage of particles have that energy, we'll have a higher percentage of particles that do collide react to form the products, and so we get a faster reaction rate. And so this is a real short lesson, just a couple things about what a catalyst is, how a catalyst works, and then evaluating the catalyst graphically with the enthalpy level diagram and with the Maxwell-Boltzmann curve. Let's actually go back to the enthalpy level diagram for a second. Doesn't matter whether it's endothermic or exothermic, it's still going to lower the reaction rate. So let's actually add a new, let's draw a new one real quick. So if I have an enthalpy level diagram that's endothermic, but we still have to, in this case, this is the activation energy. I get all the way up there. That's the activation energy right there. If you add a catalyst, you are going to change the hump, so we reduce it by a certain amount in the reaction. Now, the one thing I wanted to add to it is that the forward reaction and the reverse reaction. You can make reactions reversible. The activation energy affects both of those. The activation energy, I'm sorry, the catalyst, not the activation energy. The presence of a catalyst affects the activation energy of the forward reaction, and it affects the activation energy of the reverse reaction. This hump is constant whether the reaction is going to the right or to the left. So by adding a catalyst, you increase the rate of not only the forward reaction, but you also increase the rate of the reverse reaction. If the reaction is reversible and is a two-way reaction, you'll have both of those reactions increase in their rates. And so that's an important point to keep in mind and understand. Okay, that's it for catalyst.